let's dive right in. So you've been hearing a lot about gravitational wave data analysis, and I'll start with this really nice clean picture of projection of gravitational wave candidate events. So each one, this nice, clean, well-defined mass in blue. So of course, as you've heard, it's quite a lot messier in practice, and I'll be one of the speakers this week talking more about the noise side and why it's a much more complicated process than you might initially expect. So we're going to be talking mostly about transient noise, or what we call glitches in LIGO and Virgo. So these tend to be short duration. They can mask or mimic gravitational wave signals. And we're going to be talking about two major ways they impact analyses. So one is limiting our ability to detect gravitational waves, and the other is limiting our ability to accurately resolve the parameters of candidate events that we have detected. So just to give you a sense here, this is a nice set of spectrograms from Davis et al. And I want to draw your attention to the different timescales that we see for these noise artifacts in both LIGO and Virgo data. So here in the upper left, so this is one of our worst offenders called the blip glitch. It's very, very short duration, broadband in frequency, and has quite a lot of time frequency overlap with a lot of high mass spin candidates. And then here on the bottom, these lower two examples that you see here, different types of scattering, I want you to notice that the time axis is actually quite a lot longer for those two examples on the bottom. So these tend to trip up analyses for longer duration signals, so binary neutron stars or neutron star black hole candidates. So what we're going to talk about first is the way that these noise transients limit our ability to detect. So we're going to be focused on distinguishing between signals and noise. And then later on in the talk, we're going to be talking about that case where we have a glitch overlapping with a real signal and what we do in that case. So first, I want to give you a sense of, let's say we have a candidate. So how do these noise transients impact our ability to be really confident in that detection? So to give you a sense, so let's say we have some candidate that's got some measured network SNR. So this is the blue dashed line here is the network SNR for 15, 12, 26 as published for that analysis. And then what we do to estimate the significance is we compare this network SNR to the rate at which we'd expect the noise in our detectors to generate an equivalent event by chance. So because this noise is non-Gaussian and non-stationary and essentially impossible to model, what we do is we use the data itself. So you see this on the right here. So we've got this set of data where each one of these X's or stars is a trigger, essentially, for a matched filter search. So X's, here we have some prior knowledge that this is a glitch, and a star means this is a gravitational wave signal. And what we do is we shift each one of these. Let's say we have three different detectors here, the two LIGO detectors and Virgo perhaps. So we're shifting our data in time by more than the time it would take for a gravitational wave to propagate between detectors, which is roughly about 10 milliseconds. So now we know if we find a coincidence, it must necessarily be due to this chance coincidence of noise, because we've shifted all our gravitational wave signals away from each other. So we can do this again and again, and we can build up these histograms of measured rates of these noise coincidences. So what you should be taking away from this plot is that the higher the rate of glitches, especially glitches that overlap with a lot of time frequency features, like we saw in the examples in the last slide, that overlap with our gravitational wave templates, the higher rate of glitches that we have, the more we expect this background to pile up. And actually, the difference between these two backgrounds that you see is that for one, we have not done anything to identify and mitigate these noise transients. And in gray, we've been able to veto away data that we know is really likely to cause false alarm events. So let's get a sense of the glitch rate from our very most recent results paper. So this is from GWs+3, which just came out very recently. So the top two plots here, I'm going to focus on LIGO Livingston, since that's closer to my own research. and LIGO-Hanford as well. Virgo also similarly shows trends in time and glitch rate that are related to the weather. But let me walk you through what we're seeing here. So this is the rate of glitches per minute. And then this is over the entirety of O3b. So this is the data that was used to form the last catalog that just came out. And what I'd like you to notice here is especially relative to averages from previous observing runs. So this is O3b here, O3a, and O2. We've got these excursions where the glitch rate in both of these LIGO detectors is quite a lot higher than the averages in previous runs. And this is driven by these two types of glitches that we were actually looking at before, these two longer duration types of glitches. So these are driven by light scattering off of moving surfaces in the detectors. And so this is essentially the classic version. And then here we've got this additional modulation, and these types of glitches can go on for many, many seconds. And we'll really get a sense of that in a couple slides. So we were able to improve this. So the commissioners at LIGO Livingston and LIGO Hanford were able to essentially install into the control system a way of keeping some of these shiny surfaces stable relative to each other. And this really helps with the slow scattering that you see here. So this drops way off for Hanford. The overall glitch rate drops way off since slow scattering was dominant at Hanford. For LIGO Livingston, it's dominated by fast scattering, so it doesn't help as much. You still see this great big rise in glitch rates that actually tracks this microseismic ground motion, or tracks the weather. So now we're seeing this on the scale of averaging over months, and I want to show you now what it looks like on the course of a day. So what you see here, so this is what we call a glitchgram. It's for 24 hours, and each one of these dots is a glitch. So the color represents the signal to noise ratio, or how loud the glitch is. And what you see here is over the course of the day, we get this increase in high SNR glitches starting at about 20 hertz. So these are actually scattering arches, and I'll show you a spectrogram back again on the scale of seconds. So each one of these dots represents a scattering arch that can look like this, that can extend well up into the gravitational wave analysis band. And so we will regularly have days like this where it really is about once every other second we have a glitch. And that glitch could potentially be overlapping with or very nearby to a gravitational wave candidate event. And we also see that a high rate of glitches can cause false positives. So I'll give you a sense of that here for our offline searches. So this is after we've had months and months to analyze the data. These are gravitational wave candidates that were reported to be found to be due to noise after we examine the auxiliary data and data surrounding the candidates. So here are the results from GWTC1 and GWTC3. So on the order of 4, and these are both marginal event tables. So we didn't find any candidates due to noise in our confident event tables. But on the order of 4 for GWTC1, there were none found in GWTC2, which was the first half of the third observing run. And then at 3, so each one of these asterisks indicates that this is a candidate found to be due to noise in GWTC3. And I'll also say here that this is for the offline analysis. So for the online analysis, we did have a rate of retracted events that was hovering at right about 50% for the beginning of O3b, so really quite high. And I'll show you an example of a candidate found to be due to noise. So this is one of the O3b candidates from February 23rd. And this is a spectrogram, again, frequency versus time. And we see a lot going on here in terms of glitching. We've got some light scattering happening here at lower frequencies. And then this GIF is showing you this orange signal track here. This is following the track, the merger track of the candidate event, which is leading right into this, what we call in a LIGO detector characterization, a whistle glitch. And we see these whenever we have some kind of a system in the detector that's using modulated radio frequencies to control some aspect of the interferometer, that's sweeping through some static radio frequency reference, usually. And what you see is essentially this beat note that sweeps down and back up again. They can be very short. They can span the entire frequency range of our gravitational wave analysis. And they can look very much like a merger, as we see here in this case. So this is to give you a sense of the menagerie of glitches and the different ways that they can mimic gravitational waves. And now I'll give you a sense of a few projects that are happening here at UBC to allow us to better distinguish between signals and noise. So this first one is being led by an undergraduate student here at UBC, Serafim Jeroff. So he's employing the gravity SPI algorithm. So this is an image classification neural net. So it intakes these spectrograms that we've been looking at, these time frequency spectrograms, and then it outputs some classification that either this time is best representative of some particular class of glitch or a chirp. So the idea here is to make this analysis, which is purely based on the time frequency morphology of the data, safe to use for not rejecting real CBC candidate events. So essentially what he's done is he's simulated many different gravitational wave signals and run gravity SPI on them and tried to see what the classification is. And we're really targeting here examples like this that you see on the bottom, where you have a very high mass gravitational wave signal. So this is really pushing the boundary of what we expect we might be able to be sensitive to in the near future runs. So this is well over our highest mass detected signal, about a factor of 2 or so. But essentially the goal is to compare these high mass signals to real kinds of glitches that share very similar time frequency morphology. So this is an example of a real low frequency blip glitch in LIGO-Livingston. And I'll show you his results. So this is essentially for the performance of gravity SPI in O3. And then what you're looking at here, so these are all simulated signals. And what you're looking at is the primary mass or the heavier mass versus the secondary mass. And then gravity SPI's confidence that it's either a chirp on the left here or a low frequency blip on the right. And you'll notice that there's some missing parameter space here, and that actually goes to these longer duration glitch classes that we've been talking about before. But gravity SPI, it actually does pretty well for what was in the training set. So there are originally only about 60 examples of simulated signals that were all right in about this range. So roughly like 150914, the first detection, but all had total mass below about 100 solar masses. So what Serafim did was he enriched this training set with hundreds of more examples of high and low mass gravitational wave signals, but focused on introducing a lot more examples of higher mass signals. He worked with Sitsoni to retrain this model. And then this is now the performance of gravity SPI, where we're doing much, much better. We're above 50% confidence that these simulated signals are indeed chirps, going all the way up to about 200 total solar masses, which is about the end of the range that we expect we're going to be able to detect these in the next observing run. So this is very promising. And once gravity SPI is trained, it really runs very quickly. So this is something we could conceivably employ to inform some of these open public alerts and rapidly respond to these candidates. Something else that Greg Ashton is leading, along with contributing students from UBC. So this is a projection of glitches onto the parameter estimation space. So essentially running parameter estimation on glitches and trying to use that as a feature set to distinguish between signals and glitches. So here's an example of 3 different types of glitches. So what you're seeing here, so these are different posteriors in a parameter space. So this is mass ratio and chirp mass, and then a primary spin and chirp mass, and then primary spin and mass ratio. So we can see these different projections of how real gravitational wave signals, so those are the dots in blue here with the corresponding error bars, are projecting onto this same space as these examples of glitches. And so what Greg, Sarah, and Nico have done is for each detector, so we've got Hanford and Livingston blips, Tomtes, fast scattering, but also scattered light here. So these are each of the different colors. You can see that, especially if we look at the properties of these detected signals, we see some familiar areas of overlap where we've got some of these very high mass signals intersecting with some of these expected parameter space regions, like high mass signals of Tomtes, for example. But the hope here is that we could conceivably get some kind of a probability that a candidate event most closely aligns with a glitch parameter space or a signal parameter space in the future, if we can do as John has discussed in the most recent talk and run PE very quickly. So another thing that I'd like to talk about is more along the lines of open public alerts and really rapid analysis. And I'll motivate this by talking about the first successfully issued automated open public alert in 2003. So this is on May 18th, 2019. And this is a candidate that initially looked really, really promising. So the sky map was extremely well localized. It looked like it might be most likely to be 10 megaparsecs closer than 170817, the BNS merger with a detected kilonova counterpart. It had a 100% probability to contain a neutron star, which would make it likely to produce a kilonova. So maybe the only red flag that was obvious here is that the false alarm rate was really quite high for something that would be so close. But there was quite a lot of follow-up invested in this event, and it did turn out to be due to an earthquake. So this is a spectrogram for LIGO-Hanford. So this is frequency versus time. And I want to highlight here that the time scale is much, much longer duration than what we've been looking at. So this is on the scale of a couple minutes now, as opposed to a couple seconds. And in pink here, so this is the merger time of the trigger. So it would have swept up just like this. And it's really tricky for the searches to deal with cases of noise like this that are unique, that are essentially only happening once in the entirety of the span of estimated noise background that they're looking at. So something that a student here at UBC is working on is thinking about how do we detect and characterize these noise features that can be really long duration and trick the searches, especially that are looking for these long duration types of signals that are really interesting for multi-messenger astronomy. So this is a study led by Julian Ding, who's a final year honor student here at UBC. So he has employed this temporal outlier factor that converts gravitational wave strain, so this is strain amplitude, Whiten strain amplitude versus time, into essentially this TOF score. And what it does is it projects the data into some n-dimensional parameter space, like you may have seen with KNN clustering, but then it also enforces this penalty where you're looking to maximize your TOF score by only rewarding points that are close together, both in parameter space and also in time. So I'll give you some sense of what that looks like. So here, for the same example we were just looking at, so this is this n-dimensional parameter space projection, and then it's both points that are well localized or outliers in this dimensional parameter space and also localized in time. So they correspond to this bend that you see here. And this has actually worked pretty well. So here Julian's applied this scheme to the same earthquake example. So here we have frequency versus time again, and he's run this temporal outlier factor algorithm with different window lengths that we found are useful for different timescales of glitching. But 120 seconds actually does a really good job of capturing something long duration like this earthquake. So here we see TOF is successful in identifying and resolving an earthquake on the order of about 20 seconds or so that would have captured the data that resulted in this false positive open public alert. So this seems fairly promising, and it's an avenue that we're working on pursuing for the next observing run. And then one other project that I want to mention involving open public alerts is what's called GW+Skynet. So this is a project that was led by Miriam Cabrera, who is a postdoc here at UBC. And essentially what she did was she used the coherence that's encoded into the sky map as a distinguishing feature between signals and glitches. So she's got some nice examples here of both retracted and unretracted events, where even for events that are retracted, so on the order of half an hour, 20 minutes, you're still seeing telescope time that's being invested in following up these events prior to the retraction. So GW+Sky, once it has a sky map, can run essentially instantaneously and produce a classification, whether or not this is a true gravitational wave signal or the likelihood that it is a glitch. And when she ran this on O3A events, she found that GW+Skynet correctly predicted about 10 of 22 retracted events, which would have been a 50% improvement over the initial information that we had available for open public alerts in O3, and then also successfully predicted 6 out of 6 unretracted events that were published in the GWTC2 catalog as not likely to be astrophysical. So this is something else that we're pursuing for the next observing run. So this takes us to the end of what I had in mind to discuss in terms of distinguishing between signals and noise. But there's a lot of other important work that's happening. So Patrick Godwin will be talking tomorrow about a very important method that uses auxiliary sensor data. And then, of course, there have been a lot of other talks this week thinking about improving the performance of the detectors and mitigating noise. So this is a small piece in a much bigger puzzle, and a lot of people doing great work on these efforts. So next I wanted to take our attention to a follow-on from John's talk and think about parameter estimation from the perspective of noise. So as he mentioned, so essentially what we do to model our data is we assume that it is a sum of the signal, so through the lens of our detector network, plus some detector noise, where that noise, the way that we construct our likelihoods, we expect that noise to be Gaussian. So we expect the residual, if we subtract our signal model from our data, to be consistent with Gaussian noise. And just to give you an impression of sort of what this looks like in the same spectrogram language that we've been looking at. So here's an example of a spectrogram of Gaussian noise and non-Gaussian noise. So especially in this range of about 25 to 65 or so hertz. So what happens when this isn't true? So what happens when we have non-Gaussianity in our data, especially when it's overlapping with this time frequency track of our signal? So how do we overcome this challenge for parameter estimation? So I'll start with our most famous example of a mitigated glitch. So this was for the 170817 detection. You can see the signal track here running right through this very, very loud glitch. So this really short duration glitch is actually the easiest case for us to mitigate. And we have a couple methods here that we're showing. So one is this gray line you see here. So you apply this inverse Tukey window to zero the data smoothly out around the glitch. And this is what was used to produce the sky map that was used to detect the kilonova for this event. And then if we have some time, what we can do is we can model the glitch with wavelets, which is what Bayes-Wave does, and what we've used to produce these glitch subtracted frames in O3. And then we can subtract this glitch model right out from the data, just excising the glitch itself in cases where it's easy to model, and that's a big if. So to give you a sense of how often this happens, so here's a list of candidates that have required glitch mitigation. So this is as a fraction of confident events. So you can see it's actually a pretty high percentage, so 25%, 20 to 25% for O3b that have required some kind of mitigation. So there are a few different methods that we employ. So we can try this glitch modeling and subtraction. And in cases where that's not effective, something else we can do is limit the analysis range. So force the analysis to not look where the glitchy data is. So let me give you a sense of what this could look like. So this is a real example for a candidate event that had glitching happening in both LIGO detectors. So both Hanford and Livingston had glitchy data at the time. So we have a few options here in terms of what we can do. So for Hanford, what we could consider moving is, so here's in this orange dashed line, this is the nominal analysis region would run from about 2 seconds before the merger time to 2 seconds after. We could force the analysis time. We could conceive of forcing the analysis time to cut out this glitchy data. We could also enforce that the frequency window that we're looking at excludes this glitchy region. So that would be roughly at about 50 or so hertz. We could also try glitch subtraction. And here for Livingston, that becomes really important because we do see this a lot of overlap here between the signal itself and the glitch. And I want to talk a little bit about the method for doing this. So how do we be sure that when we're subtracting power from the time series that we're not subtracting any signal power? So here's an example of glitch subtracted frames. So this is from O3. We also expect to employ a similar method in O4. So this is the same event that you see here for LIGO Livingston data. So this is the raw data, and then this very subtle difference here is the deglitched frames produced for this event. And we use the Bayes wave algorithm here. And what it does is it uses wavelets to model both the signal and the glitch, but it requires that the wavelets are coherent for the signal model and incoherent for the glitch model, which is how we can do some to distinguish between signal power and glitch power. And in O3, so this was an unautomated step. So all of the deglitched frames were produced by hand. So I said by humans plural, but it was really just one. It was the hero, Tyson Littenberg. And I say this because each one of these, so of the tens of examples that we saw on the last slide, those all took on the order of 3 months to produce. So coming back to very good points that John was making in terms of thinking about speeding up PE and how long it can take parameter estimation to run. So in O3, we did have this 3-month bottleneck step before the data was even ready to run PE on. And I'll give you another example of that in particular. So this is one of the neutron star black hole candidates that was published in the discovery analysis of 2 neutron star black hole candidates. So what you're looking at up top, so this is the original data with no glitch subtraction at all. And then here is the signal templates. And then below, so this is the data again after glitch subtraction was applied. And this was actually not ready for the analysis paper. So what they did is they used this low frequency cutoff of 25 hertz to exclude the data below this region. But this did, of course, exclude many cycles. So some SNR of the signal as well. So we eventually moved to the glitch subtracted frames to reanalyze this event for GWTC3. And you might be looking at this and noticing, well, it does still look like there is some excess power here. So how do you know when this is now consistent with Gaussian noise? So how do you know when your glitch subtraction has achieved the goal of this residual noise being Gaussian? So we attempt to quantify the answer to this question. So how Gaussian is Gaussian enough for parameter estimation with a couple of different steps. So one is to identify these glitches that could overlap with the analysis window. So not just the signal track itself, but anywhere within the analysis window. And here are a couple different examples from LIGO Livingston, where t = 0 here is the merger time of some candidates. And in 03, we performed the step for every single candidate, and this was all done by hand, by humans, rota of event validation volunteers. And automation of this step is certainly a long-term goal, since this step alone can take on the order of 2 or 3 weeks. And then once you have that time frequency window identified, so those are the red boxes on the last slide, what you can do is compare the power spectral density in that region to some reference quiet time that you know is representative of Gaussian noise. And then, so here's an example of this here. So we've got strain amplitude versus frequency and a reference time in orange, and then a measured PSD from the example on the last slide for one of those boxes. And focusing on the frequency window that you have highlighted, you can measure with a p-test. So how consistent is this with Gaussian noise? How likely would I be if I took a draw from Gaussian noise based on this reference PSD to get something that looks like the blue curve? So Derek Davis did a great job automating this test for 03. So we expect to stick with this or something similar in 04. And this was a huge speed up in our workflow to have this step automated. And then once you have that answer, so for example, this is very clearly not consistent with Gaussian noise. But once you have that answer, then you can start thinking about what your options are. So our preferred method is to keep applying deglitching, keep trying to employ Bayes wave to get this consistent with Gaussian noise. But if that's not viable, then we need to start considering other options. And this is a test, this step 3 test, where we're comparing these different mitigation methods. So each one of these curves you see here has a different mitigation method applied. So there's a Hanford, Livingston, and no Virgo data, so just Hanford and Livingston. And the number you see here is the low frequency cutoff. So below which we're completely excluding the data in either Hanford or Livingston. So we've got different combinations here. We've got 20 Hertz, which is the nominal analysis range. We've got an F-low of 45 Hertz for Hanford, 40 for Livingston, and then also anywhere that you see DG are examples of deglitched frames. So we're comparing all of these methods to the raw data, and we're looking at how the parameters as seen through the lens of PE are changing as a function of this input data. So this is the posteriors for chirp mass, for example. And then we also look at how much network SNR we're losing, depending on the different mitigation method we're choosing. So for example, when we increase this F-low, usually we expect to see this to shift a little bit. And then we do this cost balancing here. So is the network SNR that we're losing going to be worth the shift that we're seeing? And you can see quite a substantial shift in the accuracy of PE here. So in this case, the answer would certainly be yes. So the mitigation method that gets us closer to what we're seeing here for the estimated chirp mass with mitigation methods is worth on the order of 20%, 10% drop in network SNR. So a really promising method for speeding this up, this entire workflow up in the future, is work that was recently published by Katerina Cețianu at Caltech and the Bayes wave team. So essentially what they've done is they've replaced a key part of this Bayes wave algorithm, which is the signal model, with CBC templates. So they're no longer using wavelets there, and this makes the process a lot faster and more automatable because it's much safer to model the signal with CBC templates than with the same wavelets that are used to model the glitches. So what you're seeing here in these plots, so these are 2 different examples of problematic glitches. So on the top is a blip glitch, on the bottom is light scattering, frequency versus time. And you see here a simulated signal that's injected into this data. And we apply the glitch modeling and subtraction. So that's this frame that you see here for both cases. So we're seeing that this does a really nice job, both for what we expect. So for the blip glitch, this is really well captured by a wavelet basis. But also we see that it does this really great job for the scattering arch, which is excellent news and really exciting for potentially turning this from a process that takes a few months to one that we could potentially run automatically. And then here, the signal model is subtracted, and we're left in both cases with something that's consistent with Gaussian noise. So this is really very exciting. And then I also wanted to talk about another initiative here at UBC. So this is thinking more broadly about the impact of glitches on parameter estimation. So essentially what the study does is it injects some simulated signal, and then it drags that signal through some known glitch. So for, in this case, this is actually a thunderclap at LIGO Livingston here. And what we hope to map is both the variance in the posteriors through the lens of parameter estimation for this quiet time. So this is sort of our control as this simulated signal is scooting through this quiet time here. And then also to map what happens as it moves completely through the glitch. So we're hoping really to map out where is a region that we expect to not be affected. So where is it safe to run PE relative to the merger time, and where we see this signal power from the glitch, and where do we expect to see these differences? And so this is for a different type of glitch here, but essentially what you're looking at, so for the spectrogram that captures a glitch like this flip glitch, we run a full parameter estimation analysis, and we can produce these posterograms where each one of these time steps is a full posterior for some parameter. So for this example, it's trip mass. And we can see as we walk this merger time past this glitch, how is this changing the posterior? When are we not resolving the correct injected parameter correctly? And then also we can look at this in terms of how does this compare with match filter searches? So this is recovered new SNR by PyCBC. For the same merger time as we're walking this past the glitch. And even here you can see that the impact on parameter estimation, at least for trip mass, is much, much more well localized for a short duration glitch like loop glitches than it is for a matched filter search. And we can also perform some statistical analysis with Jensen-Shannon divergence and different ways that we can add this up for different parameter estimation parameters to get this overall effect score, this impact score as a function of time. So with that, I would like to sum up by reiterating that this is an extremely difficult problem, but a really vital one. So if we want to give John and his team a fighting chance at making good use of these parameter estimation speedups, making the underlying data as consistent with Gaussian noise as possible is a really important effort. So if you're doing the calculation in your head, so we've said that roughly about 25% of our events have overlapped with glitches, and you're thinking, well, we had about one per week in the last run, and we're looking at about maybe up to one per day in the next run, we will absolutely require further automation of this process. And we do have some really promising looking recent developments. So the CBC model for BaseWave, one among them, but there are also many, many other really important and great efforts that are working towards this goal inside the collaboration. So I'll point you again to some of the talks from this week, and then say that we're all very much looking to O4 and all of the challenges and discoveries we hope that it presents. So thank you very much, and I'm happy to take any questions.